I think that to get students prepared to do FEA in the real world, instructors need to be listening to real world engineers. Professors who are teaching FEA are often drawing more on their own experiences as researchers. What they're modeling might be pretty simple in some ways from an engineering point of view, right? That you're not dealing with something that physically would have a combination of 1D, 2D, and 3D elements, or you might not be dealing with contact. Way that you're doing simulation and research, the workflow that for that is totally different from the workflow for doing simulation for design. Professors who are only figuring out how to teach FEA based on their experience of having done simulation as researchers, they're doing great at helping people get into grad school. But there is a really tough adjustment when students get to work. And so when things didn't work out for me, I wasn't sure what I was supposed to do. And I had to like Google around, find a manual that was like 2,000 pages. And I'm digging through this PDF to figure out like, what is augmented Lagrange really doing, right? My point is that I was dealing with experiences that made it really easy for me to do some really complicated stuff. And then when I got confused, it was not obvious where I should be going for help. That convinced me that it is essential to find the right question and to find the right model for the exact question that you have. An engineer who's using Apex and Nastran is thinking about simulation in a very different way from an engineer who's using an FEA tool that's built into a CAD package. I've come to realize more and more and get really excited about how engineers who are doing modeling with Apex and with Nastran, performance is extremely important to them. Right, to be able to get a good model time, to be able to get reasonable accuracy with the coarsest mesh that you can get. And so a lot of the choices that engineers are making when they're modeling with Apex and modeling with Nastran is, how do we simplify geometry? What's the question that we're asking? If we are asking, is the part going to fail? Then we need to have a really good understanding of what's happening in those fillets. But if our question is, how does this part transfer load? The fillets are not doing a lot to transfer the load, and so you can get rid of them. Man, your course is really fun. It's just the most fun that I've had with Apex. Yeah, I want to get that kind of thing in front of students. And I'm also, developing my own content that I think is going to be largely complementary to that. Some of what it takes to get good at practical FEA is not as fun as your course.
Alex Szatmary has held numerous professor roles at US academic institutions, with applied research spanning a wide range of topics across health, education, data, and applied math. He holds a PhD in modelling fluid structure interaction for biological cells and capsules, and is a registered professional engineer in the USA. Alex is the Academic Programs Coordinator at Hexagon Manufacturing Intelligence, and with his previous teaching experience in mechanical engineering, is ideally placed in helping students embark on careers in simulation. In our conversation, we spoke about the juxtaposition between academic teaching and the skills required in professional design, his work developing solid mechanics curriculum, and the academic software that is available from Hexagon. Cool. Okay, Alex. Well, good to have you on the call today.
Yes.
We've known each other for a little while now. Where are you based, by the way? I don't know.
I am in Northeast Pennsylvania. I live right near Wilkes-Barre, which is where people from the US TV show The Office would go for fun.
Okay.
It's a coal town that the mines flooded a generation ago. Yeah.
Cool. Okay. Well, I know a little bit about Philadelphia and its coal mining past, and how cities are perhaps not as shiny as they used to be. And I'm in the industrial north of the UK, which it probably shares a lot of resemblance in terms of its industrial heritage. So
right.
Here we are.
Sure.
No, that's good to have you on the call today. Cool. Okay. So Alex, your background, I believe, is mainly in academia. Just wondered if you can talk through some of the stuff that you've been doing. How has your career developed so far?
Started off at a community college studying engineering, and then transferred to the University of Maryland, Baltimore County, to finish up my bachelor's degree in mechanical engineering. Really liked it. Decided to stick around for grad school, ultimately getting a PhD. All through undergrad, I was tutoring mostly for mathematics, but also for physics and engineering courses. Really liked it, thought that I would get into teaching. And if you want to teach engineering, especially at the college level, normally, the PhD is the smoothest way to do that. And so that's a lot of what got me into getting a PhD.
Okay.
Along the way, I got really interested in doing research. And my research was in modeling the mechanics of red and white blood cells. That's what I was doing in grad school. There's some interesting fluid structure interaction problems there.
Okay.
And then I realized that for me to get good at that, I wanted to go be in an environment that was really focused on biology. And so I did a postdoc at the National Institutes of Health. And that gave me more research experience, and was a really formative point for me in figuring out my own philosophy on simulation. And I also got some teaching experience, and that led me into teaching at small liberal arts colleges. And so that was an environment where I really got to focus on high quality teaching. That was the thing that was the most important about the job. And then unfortunately just didn't have the bandwidth to be doing a whole lot of simulation research, but I was teaching a lot with it.
Okay. Can I ask? Sorry. So in your undergrad, what degree subject did you study then? Were you biology?
Mechanical engineering.
Okay, so it was mechanical engineering, and then
I haven't taken a bio course since I was 12.
Okay. So how did you transition into that then? How did that look at that time?
Yeah, that my graduate advisor was in mechanical engineering, but he had grant funding from the National Institutes of Health to do biomedical research.
Okay.
And we had some collaborations with people who were really knowledgeable about the bio end of things. And, if you're curious and you read, you can figure out a lot of it yourself. And there is so little simulation of cell mechanics or cell signaling that's being done from an engineering perspective that engineers who don't necessarily know a lot of biology can still do really important things in biology as long as they're able to work with people and really conscientious about doing the studying that they need to do to be proficient.
Yeah, gotcha. Sorry, I cut right across you there when you were talking about how you then moved into teaching. So how long were you involved in teaching in an academic environment then? How many years?
A total of 7 years.
Okay.
And most of that was starting a mechanical engineering program. The school that I was working at did not have ME before that point. And I was the first hire. I was the only ME on staff for the first 2 years. And so I taught almost every engineering course.
Wow. Okay. You must have been busy. How many students did you have on that first couple of years in the college?
It's kind of funny. For the first 2 years, my median enrollment was 1, that we had one student who had switched in from another program. If we could graduate one student, that would make us eligible to apply for ABET accreditation, and that would hopefully really help enrollment.
Yeah, gotcha.
So we developed a really strong bond and are still in touch.
Yeah. Oh, cool. So small seeds in terms of your initial teaching in that environment then. Okay. So were you always focused on undergraduate mechanical engineering courses then? Or were you...
Yes. Yeah. Okay. Almost everything that I did was at the undergrad level, virtually everything. Yeah.
Okay. And obviously I'm aware of your work with Hexagon now on an academic coordinator level that you're involved with. So I've seen some of the stuff that you've been publishing on solid mechanics, that's fundamental to all the stuff that we do as structural engineers. So were you, presumably you were teaching solid mechanics at that stage then to your cohort?
Yeah, so I was teaching a lot based on that, but I was not actually teaching the solid mechanics course. So some of the really basic engineering courses like statics and solid mechanics were actually taught by the physics department. My real focuses as a teacher were ultimately teaching programming, machine design, and capstone design.
Okay.
In my last 2 years, half of my teaching load was getting students to do open-ended design projects. I would spend a lot of time driving out to factories with
Oh,
my
wow.
students so that, yeah,
That's
we
cool.
would try and understand what were problems that people had on the shop floor and how could machines be made that would make things go better for them.
Okay. So people are getting practical applied knowledge all the
Yes.
way through their studies then through
Yeah.
real world projects that they're involved with. Yeah. Okay. Okay. So where was well did simulation come into some of this teaching at this stage then? How did that look for
Oh,
you?
yeah, absolutely. So when I was teaching programming, a lot of the point of it was to get people to be able to do simulation.
Hmm.
Um, and that was an intro course, but students were eventually, modeling engineering systems with differential equations, numerical integration, that kind of thing. And then for mechanical design, there was a lab with it. I wasn't totally sure what to do with it, but I could get a workbook and I could get some finite element software for free. And that was something that I could have that would be a reliable win. It didn't totally mesh super well with the rest of the course, but students got a lot out of it and they got something good to put on their
Hmm.
resume.
Hmm.
Over time, I did make a stronger connection between that and the course content that really focused on mechanical power transmission. So students would model what are stress concentrations at shoulders on shafts,
Hmm.
or um, we would at least use simulation to demonstrate here's what the stresses look like in gears that are in mesh or with a sphere indenting a surface, kind of like in a rolling element bearing.
Hmm.
Um, and those are tricky things because
Yeah. Yeah.
the highest stresses are subsurface, and that's really hard for people to wrap their minds around. But if you can visualize it with FEA, it helps you get it.
Yeah. Yeah. Yeah.
And then for the capstone course, I required every student to do something substantial with 7 different, what we call ABET student outcomes. Um, and one of those is to be able to model. Now, if they did a pen and paper calculation that led to a good design decision, awesome, that totally counts.
Yeah.
But if they did something with finite element software or CFD software, that would also count, especially if they were using it to make meaningful design decisions.
Hmm. Hmm. Okay. And
So
I presume that all of the work that they were doing at that level then was you could verify the model behavior back to the
yes,
solid mechanics inputs or the equations that you have to describe those kinds of structures that people were looking at.
yeah, for sure. Or
Okay.
you could at least get close enough to pen and paper that you could figure out, is this reasonable?
Hmm. Yeah. Okay. Okay. And how did the students, they were seeing FEA in simulation for the first time. So how did they get to grips with the whole world of simulation that they were involved with? Learning the software, tying that back to the theory, understanding what that meant from a design perspective. So what did that landscape look like for you, or for the students rather?
Yeah, there was another instructor who would teach a course, an elective on FEA, like theory.
Yeah.
Um, for me, with the exercises that I had for students in this workbook that I really liked, there was not much emphasis on the theory of FEA, but there was a lot of you're going to just go through a lot of workflows
Yeah.
and try a few things a few different ways, and that'll give you a general sense for things. It
Mm.
didn't lead to people being 100% professionally prepared to do FEA,
Yeah.
but they were able to have a pretty good start. And then when they got the theory, it had a lot of relevance.
Yeah. Yeah. Okay. Okay. I mean
Yeah.
that's good, isn't it? To have, you need. I've talked about this with many people. I think we've talked about this in the past. You need some level of theoretical background. You need some level of practical application. But when those two worlds come together, and you really start to see the influence of simulation and on and the understanding of how something's working, that's a pretty powerful mix, isn't it? Yeah. Okay. Okay. Well, we've got a list of
We
questions
do.
here. So we're going to run through some of these. Thank you for giving us that overview, first of all. So, I mean, I know that you're involved with Hexagon at the moment, obviously. I think you've been with
Yes,
Hexagon for
8 months.
8 months, is it? Yeah, okay. So I think we spoke when you were pretty new in the role, you know.
Yeah.
So aside from the work you were doing with the teaching and the academic projects and what have you, how did you, on a personal level, get to grips or start to get to grips with FEA? You know, from your studies and then your teaching, how did that look for you?
Um, like, how did I develop that proficiency myself?
Yeah, 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 yeah.
Yeah. Um, I've never had a course that was all about finite element analysis, at least as engineers would think about it.
Yeah.
My graduate experience was a little more tilted towards CFD, and I'd taken a course on that. And then I took a lot of courses in the math department. And when mathematicians talk about finite element analysis, it's a lot about like, what are the underpinnings of how this works, but not necessarily how do you make modeling choices where you've got a steel structure and you need to figure out, do we delete the fillets or do we really refine the mesh near the
Yeah.
fillets? Which is a question that I think is an example of what's really hard for engineers to think about in practice, but is like not as clear as I would like it to be in most curriculum. There was a finite element component to the code that I was working with, in that the cells were represented with a bunch of linear triangular elements. And that was good enough for what that purpose was. There were, like various things like that gave me a general sense for how FEA works. I read up some to be knowledgeable to help students as they work through these FEA exercises and really understand what was going on. But a lot of it, I think I've just picked up by osmosis,
Yeah. Yeah.
Or a lot of the stuff that I'm doing every day when I'm developing FEA exercises for students. The way that I have figured that out has mostly not been from the classroom. Like, most of the thinking from that is, I might have a general sense from having done a tutorial as to how to do it. And then I'll go talk to one of our senior engineers and say, okay, the way that I'm doing that, is that safe? Is that a good way to do it? And, he'll help me, make sure that I'm totally on track. And I think that's how a lot of people are really learning how to do real FEA in the real world, especially for structural applications.
Yeah, yeah. I mean, again, we have done, and we will talk more about the whole learning process. So I believe you were using ANSYS.
That's right.
In the early days. Yeah. Okay. Okay. So how did you find actually getting to grips with the software interface? What was the UI experience like for you, getting to grips with the models that you were developing and analyzing?
Yeah. So a lot of what I was learning from ANSYS, my first experience with it was the same thing as my students' first experience. And so I was working through a lot of exercise where you would use the built-in CAD tools from ANSYS to, develop the solid models. And then you would go put it in the mechanical interface where you could apply loads and boundary conditions, do meshing, run the solver, do post-processing. And the tutorials kept you pretty well on the rails so that workflow would work well. And that's kind of how I thought that you should be doing FEA, right? Either doing that or designing a CAD model yourself in a solid modeling tool that's kind of standalone, like Autodesk Inventor or SolidWorks, and then you pull that into mechanical, and then you just go to town.
Yeah. Yeah. Okay. And did you take formal training around the software usage then, or was that you were picking that up as you were going along as well then?
Yeah, I was doing it from these exercises.
Yeah. Okay. Okay. Yeah. I mean, I did something quite similar myself. Self teaching. When you're quite early on in your career is, well, back in the day was quite fraught with danger because there wasn't, we didn't have YouTube. We just had
Yeah.
piles of manuals to go through, and it was quite a tortuous process. I mean, a lot of the people I've spoken with have said that some of the best learning has been in an environment where they have a mentor, or there are people who, like you said, talk to a senior engineer. There's people you can glean from their experience, and understand how do you do these practical techniques, what the skills, what the tips and tricks involved in developing these kinds of models, and understanding that they're working properly, and having confidence in the output. So it's a difficult process, isn't it, to jump from that, like you say, from that academic environment where people are learning theory, and then becoming practicing functional FEA engineer or simulation engineers, bringing those two skill sets together, the theory and the practical understanding. That's something that can take quite some time for people to get their head around, I think. Would you agree with that?
Oh yeah, for sure. Something that I would add as, like, here's where I hit a really big bump in the road with FEA and then learned a lot. And now it's had me thinking about, how would I have people experience this differently, is this. In teaching mechanical design, I got very interested in keyed joints. So key seats, keyways, keys. So if you have a shaft, you could mill a slot in it, an indentation, put in a key, and then you could slide a gear onto it, and the gear would have a slot that would mate with that key.
Yeah.
And the textbook formulas for how you do stress analysis on this didn't totally make sense to me. They make some simplifying assumptions that are practical. They seem to work fine in real life, but I think mistake some things about the cause and effect. And I really wanted to understand this better. So I did FEA to figure out what is the stress distribution in a key. And I've not actually seen that reported elsewhere in the literature. So I wrote a paper on that last year, and and I think that's the first thing, or the most recent thing, that we have on how do keys fail in real life. The textbook models would predict that they fail in compression on their bearing surfaces.
Yeah.
And anybody who has fixed a machine where a key fails will tell you that they fail in shear. And my model helped us understand why it is that they're really failing in shear, which is not what the textbook models would predict.
Yeah. Okay. I mean, just some of the things that's come to mind on that, looking at contact behavior and stress distribution, detailed stress distributions around those contacts is not a trivial exercise, is it? Especially where you've got geometry changes in where the key fits, as it were, and then the load transfer through the contact interface. So there's quite a bit going on there, isn't there?
Oh, geez. Well, now you're telling me that. That is not the impression that I got from the workbook that I was using.
Okay.
That in my previous coursework, they never talked about contact. The math department doesn't know about contact.
Okay.
In the workbook, because ANSYS makes it so easy to do contact, and because contact is so interesting, in the first time that you do an FEA, I think it's like in that first set of exercises, you're modeling contact in threads between a nut and a bolt.
Okay.
And if you follow it step by step, you can do it. You just might not have been able to figure that out when all is done and said, right? And so I was trying to take the experiences that I'd had where I'd worked out contact, been told how to do it step by step for a nut and a bolt, for two gears, and then apply that to a different situation. And my model wasn't converging, and I couldn't figure out why not. So the way that ANSYS is set up is they make it really easy for you to turn on some really powerful things without necessarily knowing what's going on. You can run nonlinear analysis without a button saying, I want to use the nonlinear solver, right?
Okay,
You say, I'm doing contact. Or you say, here's some material properties that are taking you up beyond an elastic limit. And ANSYS will just figure out that you should be doing nonlinear, but they don't make you ask permission to go do nonlinear.
Okay, that's interesting. Yeah.
And so when things didn't work out for me, I wasn't sure what I was supposed to do. And I had to like Google around, find a manual that was like 2,000 pages, and I'm digging through this PDF to figure out like what is augmented Lagrange really doing, right? And then I was able to figure out that I, was using the right contact algorithm. The reason why I was getting, the model not converging was because I had something a little bit under constrained, actually.
Yeah.
Um, and then I was able to do the problem solving. But my point is that I was dealing with experiences that made it really easy for me to do some really complicated stuff. And then when I got confused, it was not obvious where I should be going for help.
Yeah, I mean, following the tutorial step by step gives you some confidence in the workflow, but it doesn't necessarily mean you've fully understood it, and certainly a lot of my best learning has been when things have gone wrong, because that's when you've got to go and figure out what's going on, haven't you? And it can be difficult if you're not in a situation where you've got older or more experienced engineers that you can ask on these things, so no, that sounds pretty interesting. Okay, so just looking at the list of questions, so we got one here. What's the most amazing thing you've seen in the simulation? So I asked this to many different people that I speak to on the podcast, and this can be a physical product, it can be a workflow design, it can be software, whatever. So what sort of things are impress you with simulation, and where do you see simulation used badly, or what are some of the worst examples? So have you got any ideas around those topics then, Alex?
Yeah, so I want to talk a little about a couple of models that I've worked on.
Yeah, certainly.
I've seen other simulations that people have done, and they're really amazing. But I guess because I know what went into them, they're exciting for me. They're special to me.
Yeah.
So when I was at NIH, I was trying to study how white blood cells respond to bacterial infections, because they can sense gradients in molecules that are released by the bacteria and respond to that in a directed way. We call this process chemotaxis. And as they're doing that, they can actually communicate with each other. The white blood cells can, by releasing signaling molecules that diffuse and tell the white blood cells which way to go.
Wow, okay.
So the really engineering half of that model was the diffusion equation that led to the signaling molecules moving around.
Yeah.
But I also developed a more biological model based on experimental data of, if a white blood cell is dealing with this concentration and this gradient, what is the probability that it's going to be going in the right direction? And what is the probability that it's going to be going at 45 degrees from where it should be going, which is still pretty good on average. In real life, these cells don't move in a straight line. And after I got the model working, I was able to show paths taken by ensembles of 100 white blood cells. And I would show it to biologists, and they would say, "Oh, so is this experimental data?" And that's when I knew that I had gotten things really dialed in.
Okay, yeah. And was this stuff that you were writing code to understand these things then?
Yeah, I built it all from scratch in Python.
Okay, and how about the visualization of what you were looking at?
I made the plots myself in Matplotlib.
Yeah. Okay. And what about stuff that you've seen with commercial FEA tools then? Anything, through your experience with Hexagon, have you seen, interesting things or stuff that you'd like to talk about that perhaps people might want to hear?
Yeah, there's a lot of really exciting stuff. I think a lot of what excites me about simulation at Hexagon is how broad what we have to offer is. There are other people who are really knowledgeable about, why the Nastran solver for rotor dynamics is really great. I just have to take their word for it. That goes over my head. But when I found out what atoms can do for modeling linkages, like just for modeling simple linkages, that was really exciting for me, because I had taught linkages, and I had taught it using MATLAB code that used complex numbers to figure out how they move, or Excel spreadsheets that were really based on trigonometry. And Oh man, if I had to do it over again, I would have been teaching linkages with atoms. It is just so much more fun, and you get a much more visual experience
Yeah,
of
yeah.
how they work. And man, it is really tough to make people just appreciate linkages in the abstract. But if they have an easy and fun experience putting it together, that helps them learn it better.
Hmm, absolutely. Yeah.
Yeah, yeah.
Okay. And
Um,
what about some? I think you mentioned before we started recording some of the worst examples of simulation. I think you were pertaining to situations where people are not really understanding how the models are behaving and verifying the models properly. Have you seen
yeah.
any examples of that where people have fallen over with the work that they're doing?
Well, I have, but I don't want to blame other people right now. I'm going
Okay.
to talk
Okay.
about what was just the biggest dead end for me, but it really led to me having a different view on how to approach simulation. So I was modeling white blood cells. This was in grad school, modeling white blood cells forming adhesive interactions with blood vessel walls or with microscope slides that were coated with molecules. And um, so I was modeling the 3D fluid dynamics going around the white blood cells. I was modeling the cell membranes as, using finite element, and these things were coupled, they were varying over time. And to get good results, you would need to take about 1 million time steps to model 1 second, which is like a
Wow.
biologically relevant period of time. And that was even with a pretty coarse flow field. Um, and so on the supercomputer, for me to get a batch of data that was rough, it would take a day. And for data that was a little nicer, a little more credible, it would take 2 weeks.
Wow. Okay. And this
And
is using commercial CFD tool then,
oh
or
no, this was using in-house code written in
wow.
Fortran by the grad student before the grad student before me.
Yeah, okay, okay.
Yeah, did I say in Fortran, uphill both ways in the snow? Um,
Okay, yeah.
so um,
So what were some of the pitfalls that you saw with that then? What were the problems?
well, one was we didn't have a really great question that we were asking. The question amounted to, is the deformability of the cell membrane important in how quickly the cell rolls? How quickly the cell rolls is really important biologically, because if the cell rolls too fast, it doesn't actually stop near an infection site.
Hmm.
That this adhesive interaction is to help the white blood cells put on brakes in the vicinity of an infection. Um, so the question of like, does it matter how much the cell body is deforming, doesn't really correspond to a disease state so much. And it was just not a question that like biologists or physicians were really concerned with. Another big problem with that is that it was a problem where there was a tremendous degree of uncertainty, that there were lots of biological parameters that we were feeding into the model. Like, what are the mechanics of the cell membrane? What about the inside of the cell? We were not modeling that explicitly. The white blood cells are covered in hundreds of protrusions, and those can stretch from being just a tiny fraction of the length of the cell to over the cell's body length.
Hmm.
Um, and there are multiple types of chemical reactions that are happening. This is surface chemistry, which is hard to model. And the reaction rates for those are pretty well known, but not as well known as we would like. When you add it all up, there's a tremendous amount of uncertainty. Several of the parameters in the model were not known to within an order of magnitude. It's still meaningful to do modeling when you have a lot of uncertainty.
Hmm.
But if you've got that much uncertainty, I don't really think that it's worth it to be doing a model that takes more than 10 minutes to run on a laptop.
Hmm. Hmm. Hmm.
And because it was taking me so long to get results at all, it made it really hard for me to troubleshoot, for me to find patterns, to be able to, come up with deeper questions to be asking of the model.
Hmm. Hmm. But can I
Um,
ask, were you able to
yeah.
do any physical validation or correlation of your models against some other data source then? How did you do that kind
Yes.
of thing?
We had some collaborations with experimentalists. A lot of what I was
Hmm.
doing was reductionism. I was pulling parameter numbers from the literature And then there were other experiments in the literature on average, here's how fast a white blood cell rolls. And I was trying to see if my model could replicate that. Or if I could vary a parameter that might be hard to vary in real life, or vary a parameter that's not well known in real life, could I see how important it is? Could I infer what that parameter is? So ultimately in grad school, I decided to try modeling the white blood cell just as a hard sphere. That's what some other groups had been doing the whole time. And if you do that, the fluid mechanics and the solid mechanics are analytic, right? And so the model went from taking 2 weeks to running in 10 minutes. And I was approaching graduation. I was having trouble getting great results. I showed my advisor that I had developed this hard sphere model and asked him if I could use that for the part of my dissertation that I had just really been stalled on. I wound up writing half my dissertation in a month doing that. And that convinced me that it is essential to find the right question and to find the right model for the exact question that you have. It is worth it to have models that take weeks to run on a supercomputer if you really know what's going on about your inputs, and if the problem that you're dealing with is really high stakes, like designing a commercial aircraft, right? But there are also problems where if you're designing a material handling cart for a factory, which is something that my students were doing, we have a pretty good understanding of how those things play out in real life. Our partners in industry had made hundreds of these. They just needed one more. And these carts they were made of welded tube stock. And so they were reasonably modeled with 1D elements. And so my students could throw something together in ANSYS, hit solve, and get reasonable results that could help us answer questions. And a lot of what was helpful about that was identifying what were the load paths. And then if you knew what the load path was and you looked at the model result and were like, yeah, this does make sense that this is what the load path would be, then you can figure out, okay, so here are the loads on an individual beam, and go back and check that analytically. That worked out really well. So that was a case where students were making real decisions using a model that took maybe a minute to run. And that was really great too. But what it took for them to get that level of performance was knowing how to use 1D elements and being judicious in their use,
Yeah, gotcha. So yeah, okay. So the takeaway from that would be, you've got a hyper complex model that might not really represent what the physical reality is, that you can spend 2 weeks solving, versus something which is idealized or simplified in some way that can be looked at very quickly, but still give you an idea of what's going on. You might not have the same level of fidelity or accuracy, but at least you have an idea to make, or a path to allow you to make a good design decision on the work or the analysis that you've been looking at.
Yes. Yeah. And that is what has me really excited about what I do in my day job.
Yeah. Okay. Well,
when I got,
I was going to say, do you want to just give a little overview, a small overview of what you're actually involved with at Hexagon then?
Oh, for sure. So my job is to help students and professors put our software to work. There is currently not a lot of classroom curriculum that makes use of our software or helps weave it into coursework. One of my big projects was to develop curriculum that makes it so that people who've never done FEA before can do FEA as a digital solid mechanics lab when they're taking a solid mechanics course. I'm also working on helping people use atoms for multi-body dynamic simulation in exactly the way that I wished that I had done when I was teaching mechanical design or dynamics. And it is really easy and breezy to get people in and doing something cool with that. Professors just need to know that you can do that. And if you can develop a few tutorials, a few homework examples, that helps them have a much better time using our software. I am doing some things to support getting students to use our software for Formula SAE and similar vehicle competitions. that is one of the big things where individual students are coming to us and asking us for licenses because Adams Car helps them get a competitive edge. But they need to know that it's out there, and they need to know how to get started. It seems like once they are able to get started, they can do amazing things, and it really, helps them helps them do better year over year. They're really proud of the
that's really good, isn't it?
improvements that they can make.
You spend a little bit of time learning a tool, understanding the problem, and then you can see a real tangible benefit off the back of it. That's powerful, isn't it? Certainly for a student embarking on their career.
Oh yeah, and it helps them get jobs. A lot of students who are doing these competitions know that it'll help them get hired because it's valuable practical experience. A lot of people really want to get into auto in particular, and that is a really good way to do it.
I mean, what one of the things that I wouldn't say I struggle with, but in terms of the market, is that obviously I'm pushing Apex to support a Nastran workflow and the training that I do and what have you, but it's not really caught the academic foundation, if you like, perhaps in the same way that Adams might have done. Would you agree with that?
Yes. Yeah, I think that Adams has really strong potential in academia. People just need to get the word out, right? But for Apex and for Nastran, they don't have a lot of traction in academia. When I got hired, I thought that the solution would be, like, I liked that ANSYS workbook. Let's go talk to a professor, or maybe I'm the guy to make the workbook, whatever, but we'll make a workbook like that for Apex and for Nastran. But since I started, I really got a sense that those tools are built in a different way than ANSYS is, and they are built with a different audience in mind. An engineer who's using Apex and Nastran is thinking about simulation in a very different way from an engineer who's using ANSYS or who's using an FEA tool that's built into a CAD package, which is, a pretty big chunk of what people are doing too. And there is room in the world for all of these things. But I've come to realize more and more and get really excited about how engineers who are doing modeling with Apex and with Nastran, performance is extremely important to them, right? To be able to get a good model time, to be able to get reasonable accuracy with the coarsest mesh that you can get. And so a lot of the choices that engineers are making when they're modeling with Apex and modeling with Nastran is, how do we simplify geometry? Or here we've got a part and it's got a lot of little holes in it. Well, are those holes really going to make the part that much weaker? We're going to delete the holes. If we have fillets in a part, what's the question that we're asking? If we are asking, is the part going to fail? Then we need to have a really good understanding of what's happening in those fillets. But if our question is, how does this part transfer load? The fillets are not doing a lot to transfer the load, and so you can get rid of them. So going back to what you were talking about earlier, in terms of understanding the question before you dive into the model, that's fundamental to that strategy or that workflow, isn't it? Exactly.
And one of the, I mean, I've been using Apex for a long time, so I understand the whys and wherefores of how you would design and execute a particular workflow, but it's interesting that you talk about it in those terms, that a load transfer model could be completely different to a detailed stress level model. And Apex gives you that capability to idealize or to modify your geometry, your problem, to allow it to suit the analysis that you're going to do.
Yes, exactly. And I know that you have a lot of experience in aerospace. Aerospace modeling for like an entire airframe it requires a specific way of thinking about things. And I've really gotten an appreciation for how aerospace engineers think about modeling, because they're some of the people who are using the tools that I use the most. One of the things that strikes me as really different about aero structure modeling versus all the mechanical engineering modeling I was doing before that was that for an airframe, a lot of what makes the structure work is beams. That and there's this whole terminology for lots of different types of beams, like stringers and intercostals. I hadn't heard these terms
Yeah,
before I started at Hexagon because
yeah, I
it was just
gotcha.
not my world. And then you also get a lot of strength from the skin of
Yeah,
the airframe.
yeah.
Um, well, those things are really naturally modeled very well with 1D and 2D elements.
Mm,
And the behavior of a 1D element, if you've got it loaded up right, is not an approximation, it is analytic,
mm,
right? It at least will correspond perfectly to a textbook model of beam bending.
yeah.
And so for aerospace engineers, the issues that you run into with accuracy are really different from what I've seen a lot in mechanical engineering, where a lot of people, for better or for worse, are at least starting out with 3D elements, and they're modeling problems where the geometry is complicated and you're dealing with a lot of stress concentrations. So you need to have really careful mesh refinement.
Mm,
At least when you're doing like modeling of a single part, that's how you're thinking a lot of the time.
mm,
People who are thinking that way would hit a real roadblock when they're trying to move into
mm.
modeling at a higher level, doing
Yeah,
global
yeah, 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 yeah.
um,
Absolutely. I mean,
yeah,
that's a key aspect of Apex in the sense that you can handle very large assemblies and you can
yes,
idealize the parts within that assembly to give you the appropriate load path behavior, the end load through the beams and the shear load through the panels and the webs and what have you, and then also have the ability to connect parts within that assembly to give you the load path. So yeah, that's interesting that you've with you mentioned you've been involved for 8 months in only a short period. You've been able to see how those tools are there to address a workflow that is geared around a particular industry. How people model and simulate an aircraft structure. I mean, one of the things I'm just going back to the list of questions that we've got here. That we've talked about a potential, I wouldn't say mismatch or a gap, but a disparity between the learning experience that students have in academia
yeah.
versus the physical skills that they need. Well, the thinking, the workflow design, the understanding to allow them to use those theoretical skills but be productive in a job or a particular industry. So what's your thinking around that then? Do you have any particular ideas on how that can be addressed?
Like, how do we help people understand how
how,
they do
how
simulation in the
how
real
how do we
world?
bridge the gap? How do we bridge the gap? So you have a graduate who's maybe taken a theoretical course, maybe done some practical workshops, using whatever software that they've come across, and now they're thrown into uh, an industry in aerospace or space or automotive environment where they're now looking at simulation or FEA from a very different perspective. How do people bridge that gap?
I think that to get students prepared to do FEA in the real world, instructors need to be listening to real world engineers.
Hmm.
And I've been part of the problem, that I had the experience of being a simulation researcher. And if you are mostly doing simulation in grad school, you probably should be dealing with a pretty gnarly Fortran program, right? Or
Mhm.
Python or something, building it from scratch so that you know how it works down to very great detail, and so that you can come up with new types of simulation tools, right?
Hmm.
That I wasn't ready to come up with a completely novel way of modeling how white blood cells sense and respond to chemical gradients if I hadn't had the experience of doing it the hard way in
Hmm.
grad school. Professors who are teaching FEA are often drawing more on their own experiences as researchers, where they often had to build a model from scratch and where what they're modeling might be pretty simple in some ways from an engineering point of view, right? That you're not dealing with something that physically would have a combination of 1D, 2D, and 3D elements.
Hmm.
Or you might not be dealing with contact, or you might be dealing with only contact.
Hmm.
Um, and so because the way that you're doing simulation and research, the workflow that for that is totally different from the workflow for doing simulation for design. Professors who are only figuring out how to teach FEA based on their experience of having done simulation as researchers, they're doing great at helping people get into grad school, right? But there is a really tough adjustment when students get to work. There are some professors who really care about reform, who really care about making it so that their graduates are set up to succeed in the real world, and who are curious, who want to know how it's done in the real world. But the real world engineering knowledge is not always written down in a neat way that is digestible by a professor.
Yeah.
This is something that I really care about as an educator, as a professor, and now as at Hexagon. And so I would do stuff like call a bunch of engineers and ask them how they designed key seats in real life to come up with good design guidelines for my students. Like that takes a lot of work. It would be really great if we could distill practical engineering FEA knowledge into textbooks, homework problems, projects that we can give to instructors, and they can turn around and give it to students and help students think about it in the real world way.
Yeah. I mean, one of the things that I've tried to do with the courses that I've developed are to bridge that gap, whether somebody's coming in at a graduate level with very little experience, or whether they are, coming in from a different job type, for example, moving over from a design into an analysis type of role. I've tried to capture a lot of the modeling and the workflow thinking that you perhaps wouldn't get in a theoretical course or theoretical background, to give people those skills to say, okay, we need to model a wing. How do we do it? These are this is the thinking that needs to be done to design that workflow. And then these are the practical steps that we need to put in place to think about how do we model the discrete components? How do we connect those components together? How do we solve, a large model? How do we verify the behavior of that model? All these things. So those are some of the things that I've seen. I wouldn't say people are lacking, but there are far fewer resources around for people to have that practical applied understanding of simulation and FEA to make them productive in a job. I mean, you've taken my course yourself.
Yeah, absolutely. It was a great experience. That and an internal training that we have were things that really just made the light bulb come on for me on how you do FEA in a practical way in the real world. And man, your course is really fun. It's just the most fun that I've had with Apex. Yeah, I want to get that kind of thing in front of students. And I'm also, developing my own content that I think is going to be largely complementary to that. That some of what it takes to get good at practical FEA is not as fun as your course, because you have to try doing things lots of different ways and see what doesn't work well to be able to get a sense for what does work well. And a lot of what I see from your course is showing people a path that will get things to work well. But so I think it worked really well for the goals that it had. But I wasn't put into a lot of positions where I was really frustrated, right? Because it was generally pretty clear how to get to a good result, right? That you give a lot of guidance on how to do that. And people need wins, but they also need losses to learn, right?
Yeah. Okay. I mean, I'm just
not to be too mean about it, but
no. Yeah, you're right. Like we said, people's best learning is when things go wrong, isn't it? Because that's when you really need to need to understand the problem. So I mean, we've talked about many things here, haven't we? One of the last points that we had was how can engineers and industry help students gain that practical experience? I mean, I think things like internships are fantastic, aren't they? That a student can
really
get
real
experience with things. I mean, anything else that you're aside from the work that you're doing, or you're publishing stuff on YouTube, I believe, aren't you?
Right. Yeah.
Some of the exercises that you've got, and you've also got some utilities in the Apex environment as well, haven't you?
Yes, that's right.
To help out with teaching.
To help people, just get started doing FEA in solid mechanics. So they really keep you on the rails and you could do some exercises in Apex using those tools without really understanding FEA, but it at least gives you some experience with the interface and with doing post-processing. And then I also have some tutorials where people are doing it from scratch.
Okay. So
yeah, I do want to, give some thoughts on how engineers can support students in getting practical experience.
Yeah. Okay.
And especially in the US educational system, it's been a situation where for a couple of generations, engineers who are hiring engineers, engineering managers are like, man, these people coming from college are pretty bright, but they don't know how to tolerance a drawing properly, right? That they really wish that graduates had more practical experience and had a real world orientation on how to get things done. There have been some really important moves for reform, many of which are driven by industry, right, to make education better. But change is really slow in academia. So I do know that there are a lot of managers and engineers who are motivated to helping students get more practical experience. So like you said, internships are important. And I think a couple of things to make that go really well. The first is to use fair hiring practices for internships in the same way that you would try and hire a really good employee who is a new graduate or a few years out. A lot of the time people are getting into internships because they have a connection. Maybe they're somebody's nephew or something, and they come up with a project for them to do at work so that they can get work experience. But a student who already has that connection is probably going to be okay. But students who are from racial minorities are going to be less likely to have those connections, and they need more help. And they really have trouble finding internships if ads aren't posted publicly, if ads aren't at least posted on the employer's website, if employers aren't reaching out to a few different schools and actively trying to recruit people and trying to hire good interns who are going to have the right mindset for the particular tasks that they want their interns to do. And so just like you would hire an employee for a job based on, we really need somebody who has these skills, so we're going to put those skills in the ad, we're going to interview based on those skills. Simply following a rigorous process like that is a lot of what it takes to have a better, more diverse and fairer hiring process. And the more that employers do that, the more diverse applicants they get, and the more practical experience they'll be getting to people who would otherwise really struggle to get that experience.
Yeah, no, that's a good point. Absolutely. Yeah, I think things are slightly different in the UK.
Yeah,
we have placement degrees where people work, spend a year working in a company, and that's all organised by the university. So it's not up to the individual to look for those placements if they don't need to. But certainly people are able to benefit from some industrial contact in terms of their learning. Yeah. Okay. So I mean, we've covered a lot of things there. We've talked about your background, your sort of introduction into academia, simulation, teaching, and now your role with Hexagon, and also some of your thoughts around the way that simulation is taught and used. Is there anything else that you wanted to touch on before we close? Any other thoughts or ideas or anything you'd like to say in general terms?
Oh, I would just mention that there are some other ways that engineers in industry can help students get practical experience that are really fun, I think. So make connections with your local college or university. They are looking for input from engineers. In the United States, it is a accreditation requirement that you're getting input from engineers on your curriculum. And so typically like a mechanical engineering or aerospace engineering program will have something called an industrial advisory board. So if you reach out to the college or university and you say, hey, I'd be interested in helping out, they might want you to be on their industrial advisory board. And so you would be meeting with them periodically, maybe a couple times a year, giving input. And that is something that input can be really persuasive in leading to curriculum changes that make, the experience for everybody more practical. But also you can do things like sponsor design projects for students. Have them come out to your factory and design something for, your shop associates. You can host field trips. Students love going to factories, going to places where engineers work and seeing how it's done in the real world. And, you know, it makes life easier for a professor. It's one less lecture for them to prepare if they can just drive people out somewhere.
Yeah.
If you come to campus, you can give a seminar. You might even be able to give a seminar over Zoom. Talking, like to just talk about your career for 50 minutes can make a really big difference for a student, and you'd be surprised by how much attention you would get from doing that. And you know, sometimes you have to sometimes you find curious professors, people like, you know, I was as a professor, reaching out to say, how do you do this in the real world? How do I teach people about drop forging, right? And if you're willing to pick up the phone, you can, you know, at least help one professor teach things in a way that's more authentic and indirectly reach dozens and dozens of students.
No, absolutely, Alex. No, they sound like really good ideas, you know, and it's definitely something that I wish I was perhaps more involved with than when I was younger, you know. You know, and it's great that you're in a role now where you can perhaps help with some of that interaction, you know, to make people's learning experience better, but also, you know, make things more interesting for the professors as well. You know, that's
oh yeah.
No, good stuff. Okay. Before we finish, I just thought it might be worth just mentioning what software is available from Hexagon to academic users. What stuff have Hexagon made available to students?
Yeah, so again, I would say that we've got finite element packages, Apex, Nastran, Patran for, you know, typically more like big scale structural modeling, and Mark for nonlinear modeling.
Okay, yeah.
Cradle for CFD, Actrin for acoustics modeling, Atoms for multi-body dynamics, and DGMAT for modeling materials like composite materials.
Yeah.
Those are free for any student, any professor in the world. If you're a professor signing up, the form will ask you your graduation year, just put in whatever you like. It looks like it's a form built for students, but professors can use that form too.
Okay.
We also have educational licensing to make it so that you can use the software for research or for teaching purposes. And to do that, that software is available at a really deep discount, but that is the full commercial powerful version of the software.
Okay. Yeah.
And the selection for that is broader than the list that I just gave.
Yeah. Gotcha.
A lot of our software comes with an educational discount, or if it's software that you can get through something called MSC1 tokens, those are available to academics at a discount too.
Yeah. So there's a big portfolio of software available through MSC1. Yeah, I'm very familiar with that. Yeah, good stuff. Okay.
Oh, so, and like two more things. Our students who want full commercial releases of our software, who really want to be engaged in one way or another, if they are doing a competition like Formula, Baja, and they're willing to put our sticker on their car, they can get commercial software from us for free. And if you just want our software for other reasons and you want a full version, and you want to do something like start a club on your campus for computer-aided engineering, then you can become a Hexagon student ambassador.
Yeah, that's good to know, Alex. Yeah, great. So people can, you know, alongside their academic learning, get to grips with commercial software to help them understand what they're looking at, how the structures are working, and ultimately to allow them to move into the workplace perhaps a little bit more.
Yes, absolutely, for sure.
Yeah. Great. Thank you, Alex.
All right. It's been great talking, Steph. Thank you so much.
To speak to you as well. No, really interesting, Alex. So thanks again. And
thanks. It's been great talking. I really appreciate it. All right. See you.